Okay, there are many words in the title, so I will try to start motivating the whole thing. I don't know, probably I will not assume you are familiar with tensor networks or anything like that, so we'll try to go slow. Please interrupt me anytime with questions. Okay, so I will start from the end, trying to motivate the problem that we will manage to solve, at least partially, using tensor network, which is the problem of privacy in machine learning. But before that, okay, this talk is based on papers, you have the archive numbers and the persons involved. Okay, so let's start talking first about machine learning. So okay, the idea I would like to present is that machine learning and the usual type of problems that one tries to solve in quantum many-body problems are pretty similar from a global perspective. And the reason is the following. So in machine learning, one has a goal that usually is just to learn some function. And the way to do that is by saying, okay, I can approximate this function by a particular family of functions, which is the set of neural networks. I'm taking these pictures from the nice lecture notes of Michael on machine learning, mathematical aspects of machine learning. And this is just a usual neural network in which I have some neurons that are just linear functions together with some activation function, which is a high nonlinear function, and concatenate through a net. And the way in which I try to learn that function is by minimizing some other loss function that tells me when my element in my relational family is close to the function I want to learn. Okay, so that's the global perspective. And why searching on these neural networks? Okay, it's just because, at least historically, one is trying to mimic what is happening in our brain, and that's the main. In a quantum many-body problem, the goal is to obtain, one goal, the ground state of a Hamiltonian. And how? Okay, then you search on some variational family, and now you want this as a family that somehow has the guarantee that approximates well this set of ground states we would like to have. And one such family could be the set of tensor networks, because it's known that they really approximate well ground states of Hamiltonian. So we'll comment on that later. And how? By minimizing a function, in this case, the energy function. So from a global perspective, both things are somehow pretty similar in the speed. And then it makes sense that, I mean, these two fields have found some meeting points so far. Okay, so one direction is how is using machine learning techniques in quantum many-body problems. And this has received a lot of attention and a lot of success in the last years. There have been many papers, and the one particularly successful direction is to kind of train, I mean, machine learning with classical information obtained from quantum many-body systems, with classical shadows, and then use this to let machines obtain information like phases of matter in which some quantum system lies. Several papers, maybe this paper by Pérez-García and Merkel that was pretty seminal, and then this set of papers by the group of John Pressley that was also very good, a lot of attention recently. So that's probably some of this. Okay, so there is also a reverse implication. So is there a way in which quantum many-body ideas could impact in some way machine learning? Okay, there have been also some papers in that direction. A couple of them, paper in which by Miles Stoudemire and David Pérez-García, there was another paper at the same time also by the group of Ocelledets in which they use tensor networks in supervised learning, decent success, and more recent ones, showing that with tensor networks one can get, in some problems, even things which are a bit better than what you get with neural networks. Okay, so, however, in some exceptional cases, tensor networks, which is one of the maybe most promising structures coming from quantum many value systems that could impact machine learning, there have been very few cases in which tensor networks can make it better than neural networks. I mean, it's quite hard to make it better than neural networks nowadays. ChatGPT and all these are just examples of how powerful neural networks can become. Okay. But it could be that maybe tensor networks cannot be as good in accuracy prediction, but they can bring other things into the table. For instance, they could add interpretability. So we know that in tensor networks, one of the nice things is that the properties of a quantum many value system are encoded in some local tensors, and we have a lot of expertise on how to extract global features from these local features, and that's exactly what interpretability is about. So efficiency, there have been a lot of effort now in trying to use tensor networks to compress machine learning, so that now they have similar accuracy, but they occupy much less space. And now in this talk, I will see that maybe also in privacy. Okay, so interestingly, these three things, interpretability, efficiency, and privacy, are 3 out of the 7 key ingredients that have been identified, at least in Europe, on what ethically sound artificial intelligence should be. So in this sense, it could be that tensor networks could be a way to address this challenge. Okay, so let's go now into which is the type of privacy problem we care about. Okay, so the machines are now trained everywhere, and in particular, they could be trained in some sensitive data. That we want to train a machine to predict the evolution of a pandemic, COVID, something like that, and for that we have to train in hospital data. It should be kept private at this point. Okay, machines need to learn. So in the output function, there must be some information on the training data. There's no way around. But it's desirable that only the relevant information from the training data is kept in the output function. No other information is leaked from the output function. So let me illustrate this idea with just a stupid toy example. So imagine that I have a picture with cats and dogs, and I want a function that separates cats from dogs. And I train this function in 2 training sets, T1 and T2. And if I train T1, I get this function. And if I train T2, I get this function. Immediately realize that both are the same function. But the way in which I describe the function depends on the training set. So by the function itself, I cannot get any information. But by the way I'm presenting the function, I can get information. And that's something that is not desired. So that's, the typical problem that cryptography is called obfuscation. So it's the problem that Windows run every time that they want to put a patch on the market. So they detect some vulnerability and they want to fix it. In order to fix the vulnerability, they want to create a patch. To create a patch, somehow they use all the information that should be hidden to the users in the operating system. But everyone should be able to run the patch. So essentially, they should give us a circuit to run, which is the patch, that should not reveal any information from the operating system it was created from. So that's what we should be able to run it, but by running it, we should not get any information from how it was created. That's. So essentially, I mean, from a global perspective, this is saying that having an access to the internal details of the machine, for instance, for a neural network, just the parameters that define the neural network, this should not give more information than having a black box access to the machine. So you just can use it as an input-output relation. That's the ideal problem of association. So that giving the details, internal details of the machine should be not more informative than a black box access. So that's what we will do. So first of all, one may ask whether this is a real threat in machine learning. So that's whether this is something that happens. Okay, so what we did, we took some COVID database, in which the input was some patient data, age, gender, blood pressure, exactly. And one of the data was, in principle, something that is totally irrelevant for anything related to COVID, which is the parity of the data entering hospital. Okay. And then we train a machine, and the goal was to predict the probability of death based on the patient data. Okay, and we got a decent accuracy prediction, 85%. And then we try to extract from the parameters information about that irrelevant variable, which is the parity of the data entering hospital. And for that, we just created biased training sets in which 80% of the data were having points with an even parity and 20 with an odd, or vice versa. And then we decided we implemented an attack to try to learn such parity. Okay. And we got very successful attacks that in the end were essentially linear with the bias. And these were attacks that only succeeded if we had access really to the internal parameters of the neural network. I will see later, but if we ran the attack in a black box scenario, then it was like tossing a coin. Probability of that success was 50%. So after that, I mean, much more spectacular attacks came. For instance, they managed to reconstruct the exact images of the images of the training set just from the parameters of the machine. Here we have examples in which these are the images in which the machine was trained, or the ones below in which it was trained, and the ones above, the corresponding ones that were just extracted, looking at the parameters of the machine. So one can really have access even to the training points just from the data. Okay, so which is the underlying problem? Okay, the underlying problem is the following. So the information of, in our case, the irrelevant variable is erased. It does not appear in the input-output relation. But the way in which it is erased depends strongly on the training set. And the way in which it is erased appears if one has access to the parameters of the machine. So essentially, from a global perspective, the question is not known which are the different choices of parameters in a neural network that give rise to approximately the same function. So essentially, the gate symmetries in a neural network are not well understood or characterized. And therefore, it's not clear how to remove the information that's encoded there. That's the problem behind. And now, okay, now people, some of you know tensor networks, you know that indeed in tensor networks, gate symmetries are much better understood. And this was kind of the basic idea behind our work, trying to say, okay, now maybe then, if instead of training with neural networks, we train with tensor networks, then one can really use this knowledge to erase that knowledge. Okay, so now this will motivate understanding tensor networks and understanding these gate symmetries and trying to find a way in which we can remove that information, and for that we will have to find what is called a canonical form for a tensor network. That's why the title of the talk. Any questions so far before going into tensor networks? activation. Okay, so some basics in tensor networks. So we need a box-leg notation for tensors because we will have to deal with two-dimensional tensor networks, and there is no clear mathematical way to do that. But there is a very nice graphical way to do that. So essentially, a tensor is just a box with legs. Okay. Legs can point outside, and this means that this is a vector in some vector space, or inside, and this means that this belongs to the dual vector space. A matrix is an element in a vector space tensor, the dual, and then it can be seen simply as a box with a leg pointing in, a leg pointing out. Of course, it's that. Okay. Vector is tensor with a vector pointing out. This means a ket. Vector pointing in is a bra, and a matrix is So first rule of this graphical notation is if I write two tensors together, this means tensor power. So tensor product. So it's the same as tensor power, tensor product. Many tensors together is the tensor product of all of this. And the second rule is if I join a leg, it's tensor contraction. And that's simply the duality relation between one space and the dual space. The dual acting on the space. For instance, if I contract a vector with a dual vector, like that, this is just the duality. It's scalar product if it were real. Okay? So it's just the duality action. If I take a matrix and put another matrix afterwards, this is just matrix multiplication. Because a matrix is an operator, it's an input and an output. If the output is the input of the next matrix, this is composition of operators, and that's matrix multiplication. Okay. So with these two rules, I can write, for instance, our first and most famous tensor network, which is a matrix called state. And that's that. Let's go slowly through that. So how I arrive at this object? So first of all, I take the tensor below, which has three indices. So the index pointing down is called a physical index, and as I mentioned, small d. And once this index is fixed, I have two other indices, which is just a matrix. So this is a sequence of matrices. For each I, which is fixed in this leg, I have a matrix AI, which is given by the other two legs. And these other two legs are called the virtual index, and the dimension is capital D, and it's called bond dimension. So how do I get that tensor network on top? So I take this tensor below, and I put it several times. So now it's the tensor product of this with itself, let's say n times, capital N times. And now all the legs in the virtual degree of freedom, I just join one with the next. Because I had a tensor product before, the physical degrees of freedom are tensorized. And this is why this object lives in the tensor product of the complex CD n times. But now in the virtual degree of freedom, I have these matrices that can multiply with one with the next. And that's this matrix multiplication. And once I have a final matrix, I join the two legs, and that's taking the trace. I have a matrix and I contract the two legs, that's taking the trace. So this object is just simply the n-value quantum state with coefficient given by this trace of product of matrices. And that's why it's called a matrix product state, because the coefficient is a product of matrices. Okay, but is it clear now why this little tensor concatenated many times gives rise to that object at this moment? Okay, so that's kind of the basic tensor network. But now once we have this, we can play exactly the same game in larger dimensions or in other graphs, in 2 dimensions. Now we have a 5-leg object. And now we need like a 3D point of view. So there is an arrow, the red one that goes like outside of the wall. I put it in red. That's the physical one. And in order to avoid these 3D paintings, this arrow I will write as a single dot there. And now I have the other 4 legs that are the virtual ones that will get contracted in a 2D lattice. And you see now that you have all these contractions. And then I finally take a trace in each one of the lines, both vertical and horizontal. So this is what is called boundary condition, that I don't write the lines because it would be too complicated in the figure. Okay, but that's how from this single fiber tensor I get these many various states, which are called in this case projected entangled pair states. Defined essentially 10 years ago now by Ignacio and Fred as a generalization of multiple. Good. So these are our tensor network characters for today. Any question about these? Yeah, please, Marius.
These pictures, they are just giving me the coefficient for the graph, right? They're not giving me the whole state.
No, they give the state because these legs are open, so it is clear here. So each one of these legs, because they are open, this means that this is a tensor product of vectors, if you want. So this gives you the CD tensor CD tensor CD tensor CD, the same thing. Any other question? Okay, good. As a side remark, as I say, these objects are very used both for numerics and analytics in quantum many-body problems, because it's known by now that they approximate well ground states, low energy states, and thermal states of local interacting Hamiltonians. So for the 1D case, it was proved by Hastings almost 20 years ago, and there has been improvements over that. Also, it's known that these multi-spot states that are good approximation of ground states can be found efficiently. This is a result by Ferdinand probability. And okay, now in 2D, one needs to add extra technical hypotheses into the table to obtain similar results. And it's a big open question if one can remove those hypotheses. But okay, still, philosophically, same is true. Okay, so back to our problem. So how to understand and characterize gauge symmetries in multiple states. So the question is now I have 2 tensor networks. You can see them as the output of a training process in some training set that give rise to the same black box. So they are the same vector. Which are the relations, possible relations between the green tensor and the orange tensor. So there is a clear sufficient condition. So if the green tensor is equal to the orange tensor conjugated by similarity by an invertible matrix, of course, the above is true. Because if I change the green by the orange with this formula, whenever I multiply, y and y minus 1 cancel, and that's it. You don't see that. So, question is whether this is also a necessary condition. Okay, we will see later that it's not in the general case, but it is in the generic case. Okay. And by generic, we mean that the tensor is what is called normal. Normal means that after blocking, it defines an invertible map from the virtual degree of freedom into the physical. This is not Angela and Giffel has very nice recent work in which they show how fast this happens in the generic case. Okay, so let's keep for now in the generic case and think how do we erase the information present in the case. So there are 2 options, maybe more, at least 2 options. One is we would sample in the gauge uniformly, then whatever information is there is erased. Okay. And option 2, one can try to find a particular way to fix the gauge among all possible multi-spot states that give rise to the same state. So all possible such relations fix one particular vector. Okay. So both things are possible in 1D, But let's go just in this talk for option 1, because that's the one that we will generalize to 2. Okay, so given a tensor, we want to sample uniformly from all tensors of that form. Okay, there's a clear problem. Y is just an invertible matrix. And there is no way, or at least no natural way, to sample uniformly from the from GL. Okay, good. So what's the way around? The way around is that it's known that there is a canonical condition that one can impose without loss of generality in a matrix state. And it's the condition that the matrices, the set of matrices that define the matrix state, define a quantum channel, are exactly the Krauss operator of the quantum channel. This condition of the opposite quantum. And this allows to identify the set of matrix state with the set of quantum channels, and this identification is behind many of the success of matrix states that one can use now quantum information techniques. Easy, but okay, that's another story. But now, if we work under such canonical conditions, then this gauge freedom becomes this gauge freedom, in which now Y, being an invertible matrix, transfers to U, which is a unitary matrix. So if we work under such canonical condition, two matrix states are equal if and only if they are related by this equality. And now U is unitary. And this solves the problem because there's a clear way in which one can sample uniformly from a unitary group, which is at the Harris. And that's what we do. In this, one can keep adding other canonical conditions and reduce the gauge even further, just products of U1. Crucial. And as a side remark, let me tell that these canonical forms are behind many of the important applications of matrix states. For instance, they make variational algorithms based on matrix states more stable, and they allow to make computation of matrix states very fast. They allow for a nice boundary correspondence that, for instance, is behind the characterization of symmetry topological model in terms of the second component group in one dimension, and many more. That's it's not just for this. I mean, this canonical form is still useful, and as I said, the reason behind is that we can connect matrix states with quantum channels in a one-to-one correspondence. Okay, so does this work in practice? Does this idea solve the problem? Okay, well, the idea, yes. So let me explain what this picture means. So the blue is the neural network. This orange is we train with matrix states, but we do not do anything to the gauge. Okay, so again, the information is still there in the gauge. In the green, we use this canonical form to reduce the products of U1s. So we reduced already a lot the gauge, but still there is some gauge. Then you see how the information reduces. And in this final, what we do is we sample from the gauge uniform. Then you see that essentially you get 50%. So that's the picture. So in practice, this works, and one can see how this information is there. Yeah, please.
But here, what was the main goal to
Exactly, because exactly so you train your matrix state in this case with different training set with some bias, and now bias is irrelevant information. It is parity of day and the hospital, and now you would like to see whether by having access at the matrices themselves, to the coefficient of the matrices, you could extract that information. And we develop attacks to extract that information. And we show here that this information is in that gauge, so that when we sample uniformly from that gauge, the information is erased. Because now it doesn't matter from which training set you start, in one, you start with one training set with a particular gauge, you start with another one. But since you sample uniformly, that information goes down.
So you learn something.
So what we do here is we learn, we construct a matrix for the stage, and after that, we sample. And of course, this is just the typical mean after several times in which we do the same experiment. Yes, Marco, please.
Yes, I was just wondering, intuitively, it's not immediately clear to me why this depends on the percentage of the majority irrelevant class.
It's a very good question. It could be maybe because we didn't work that much in the attack. So the way we attack, we run the experiment several times, and then we create another neural network that tries to learn that information by feeding it several. And of course, we didn't make a huge neural network there because it was very costly. So it could be that the information somehow is there, but it's harder and harder to distill it, and then you get maybe larger and larger neural networks. But I mean, it's a good, I don't know. I mean, I guess that of course the larger the bias, the easier to detect. But yeah, why is linear? That's a good question. I don't know. Yes. This yes. This is the. No. Okay, sorry. What do you mean by learn now?
You make this neural network for the first one?
No, the accuracy to learn the probability of death is similar to matrix potential for neural network. That's 85%, and that's independently of that. So that's simply the attack to extract from this trained machine the information about this parity of entering hospital. But the machine was trained to try to predict the probability of death of a given patient, and for that task, accuracy is dependent on that. This is 85% approximately, both for neural networks and for matrix potential. That's simply for the attack. Yes. Yes, please.
I'm still a little bit confused. So when you say average attack accuracy, so if it's the 0.8 bias, then if you just always guess in that direction, you get the 0.8. So is that what's happening here on the line? The red line?
Because of course, if you were just that, below you will get that 50%. No? So I think you really have to, because of course this is, I mean,
but the 50% is essentially then you're behaving irrationally. You're just guessing randomly, even though you know there is a bias.
Exactly, but in principle, the machine that is trying to attack doesn't know there is a bias, and also in which sense it's even or odd. I mean, this is not known. This is not known. So it's that I mean, the attack is done in an unbiased way, even there is a bias behind. And the bias is either in the even or in the odd. So
that means that the machine didn't learn that there was a bias in the sample.
Yes. I mean,
exactly. Realize.
We didn't. I don't know if we didn't try that. We really tried to guess in the best way the parity, but that's yeah, okay. Yeah. But probably we should think more carefully on why it's linear. Yeah, it's a good question. Probably it's interesting to understand why, but that's. Any other question at this point? Okay, good. Okay, so this was done for matrix plot states in one dimension. Can one extend the same result using matrix plot states? Okay, and the answer yes, if we have the two ingredients that we need. So first, a good characterization of gauge symmetries, and second, a canonical form which reduces gauge symmetries to something like the unitary group we know how to sample from. Okay, so let's go to ingredient one. Good problem.
Igen,
so,
igen. Hát a Gina most azt mondta,
tehát,
igen, ő mondta, hogy 39%-ra
it is undecidable, given a tensor, to know whether this object is zero or not for all tori lambda. That's easy because one can easily encode the problem of whether a set of times allow a periodic time, which is known to be undesirable. So this implies that for an arbitrary tensor, gauge symmetries are undesirable, and that's bad. Okay, so there are two ways around. One is to say, okay, maybe we should look for more complicated topologies than tori. We'll do that later. And indeed, this is what is behind the undesirability, as we will see. And second, we say, okay, we can do as before and just vote for generic tensors. And the notion of generic is normal, which is the same as before. After blocking, the mapping from virtual to physical becomes an injective mapping, which is a linear. Okay, so it's known since long now that two normal tensors that define the same pairs in all tori, if and only if they are related by these gauges, and this was generalized in a work with Andras and a few others. Beyond the relation invariant case for any graph. Okay, so in the generic case, we know that the case degree of freedom is only this one. But again, Y and C here are just invertible matrices. Can we put them into unitary matrices? Is there a way, a canonical form that allows to reduce the gauge from the linear group to the unitary group? And okay, that's second main result, that there is indeed a canonical form which allows that. And the solution comes from geometric invariant theory. And okay, there is a reason for that. I mean, geometric invariant theory studies actions of Lie groups in vector spaces. And that's exactly what we have. We have just, GL cross GL that is acting on the set of tensors just by similarity conjugation. And the set of tensors related by a gauge is just the orbit of a tensor. And two tensors are gauge related if one belongs to the orbit of them. Okay, important thing, that's okay for normal tensors. The generic case we are considering, in the general case, one has to be careful because orbits are usually not closed. They are normal tensors, but they are not closed. And one has to take closures, take limits. That's very important. But again, for now, no need for that. Okay, so let's define now the minimal canonical form. Which is the canonical form. We call it minimal because it's obtained by minimizing a norm. So given a tensor, we just consider all elements in the orbit of that tensor with a closure. As I said, for the generic case, there is no need for closure. And take the one that has the minimum norm. A norm is just the Hilbert norm. As I say, the closure is needed in general, but not for normal tensors. For normal tensors, you can prove that the orbit is closed. Yeah, just simply for simplicity, with a loss of generality, we assume that the dimension D is larger or equal than D theta, so that we don't have to keep track of both D and D theta. Okay, so which are the properties of this minimal canonical form? So properties will be consequence of known results in geometric invariant theory, some old results from the 70s, 80s, and some new ones. So property one, the minimal canonical form is unique up to unitary gauges. That exactly means that minimizing this norm reduces the gauge freedom from the linear group to the unitary group. That is exactly what we want. So, in a sense, problem solved. And this is just a standard use of a couple of well-known theorems, Markov theorem and Kerfner's theorem, for this particular action. Okay, property one. Okay, this is probably useless if it's impossible to compute that canonical form, and that's property two. It can be efficiently computed. And indeed, we have two algorithms, and it depends. So there's no free lunch. So either we get polynomial in D, capital D, which is the one dimension over the precision, or we can even get log 1 over error, but we have to pay a price that it becomes exponential in the one dimension. So you choose. And why? So the key observation is that if I consider the map that maps from GL cross GL a pair YC to the norm of that object in the orbit, this is geodesically logarithmically convex. And geodesically in the Riemannian structure of this thing. So it's not just, it's like a convex function, but it's convex in the sense of the geodesics, but it's even better than convex, it's log convex. And now the algorithms are just gradient descent, or geodesic gradient descent, for the first one, to obtain this point, and a second order method using the Bayesian or geodesic Bayesian for this one. So they are just also easy to implement. The code is in the paper. Okay, so, and okay, property 3, which is useless for the purpose of this talk, but is useful for other things, is that there is an algebraic formula which characterizes being minimal canonical form. And this is simply if we impose a condition, geodesic gradient equals 0. Because of the convexity, that's equivalent. And that's a nice algebraic formula that, for instance, allows one to show that the toric code in the standard tensor network picture is of canonical form and so on. But again, it's useless for this. Okay, so there are these three properties. So just with the first two, we can solve the problem. Because now what we do is we have a Pérez tensor that we obtain by training. We compute this minimal canonical form, which is possible because it's efficient. And now this reduces the gates to unitaries that we can sample from this hardware. That's the way to go. We didn't do the numerics yet. Still need to see whether this works in practice. And the reason is that working with PEPs numerically is much harder than what is called the states. So training and all that is not as easy. So it takes, we take a lot of time to go into that, but okay, that's a good. Okay, so somehow this finishes what I wanted to say between the connection of the problem of privacy and canonical forms, and the rest of the talk is last 10 minutes. I will just go deeper into this canonical form and see what happens in the non-generic cases that so far I just put under the cap to show the totally general case. So before switching a bit gears, any question about this first part? Yes.
Is there a space also connection to channels?
Ah, good question. In principle, no. I need many questions. Maybe I ask one in the open question session after, but many questions that are known in 1D. And the reason they are known is for matrix potestates because you go to channels. They are not known in 2D precisely because there is no connection to channels. So that's a good one. So can one guarantee that this is the only case beyond the generic case, both for 2D and for 1D? Because if so, the part of the minimal canonical form is still okay. Remember that part only uses that there is some action of Sandy group, blah, 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 blah. Essentially, it's only using that this is the only case. So this part is always okay, as long as we can guarantee this is the only case. So the problem is not easy even in 1D. So in 1D, this sufficient condition is not necessary in the non-generic case. And there is a very easy example, which is the following. So I take the tensor, this is the physical degree of freedom. So this is, this is given by two matrices. So, this has dimension 2. So this tensor is 0 in the physical degree of freedom tensor, some matrix here, plus 1 in the physical degree of freedom tensor, some other matrix. And these two matrices I can take either for the orange tensor M0 equal to that, M1 equal to that, or for the green tensor M hat 0 equal to that, M hat 1 equal to that. Look that, because what I'm doing is just multiplying these matrices and taking a trace, because in both cases the matrices are upper triangular. Whatever happens in the upper right corner is totally irrelevant. Because since I'm going to take the trace at the end, only what happens in the diagonal matters. And because they are upper triangular by multiplication, what happens in the diagonal only depends on the diagonal. So if I change in whatever way the upper right corner, the matrix protestant will not see that. So in particular, these two will give rise to exactly the same object, which is the GSC state. However, even if both tensors orange and green define the same state, they are not related by a Gestalt. You can see this is very easy to see. However, that's almost true. So that's true if one allows to take limits. In particular, one can show that the green tensor is the same as the orange tensor conjugated by a sequence of invertible matrices. When we take the limit, we're going to see. Because in the limit, they are not invertible anymore. Because these objects are polynomials and the tensors that are continuous, taking limits will not affect the state. So taking limits is allowed. So this way of taking limits solves this particular example, but this indeed solves all examples. If limits are allowed, singularity conjugation is the only gauge in one. So for that, because we need to take limits, we have to change the definition of being gauge related. Another definition is that two tensors P and S are gauge related if and only if I take the closure of the orbit of one and the closure of the orbit of the other, they have non-empty intersection. So by taking limits from both sides, I can arrive to the same point. Okay, for normal tensors, this is the same definition as before, because normal tensors have orbits are closed. Two orbits intersect at the same orbit. And we have this theorem that indeed in a different language exists in the 80s. That solves the 1D case. Two matrix protestants are equal if and only the two tensors are gauge related with this definition. And moreover, it's enough to check for sizes less than d squared, where d is the moment. That's the solution. So what happens in 2D? Can one guarantee something similar? Now up to taking limits. Again, problem. We have still this undecidable problems. That's bad. But as I will see in a second, the problem of this undecidability comes from the fact that we are considering just toric geometries. That's toric. So we need to take a bit more complex topologies. So for that, we need first maybe to look for necessary conditions for two tensors to behave like that. Okay. So now, let me take a tensor P, and now I put colors. The arrows are like always, but they put colors. So the horizontal arrow is black, the vertical arrow is red, and I just consider just another element in the orbit. Now, I take many copies of the tensor, and I join the legs in any way that is compatible with colors and arrows. Meaning that arrows should behave as always, that an outgoing arrow should go into an ingoing arrow, and red arrows should be only mixed with red arrows and black arrows with black arrows. Okay? So for instance, that's one possibility. Like three tensors together, and I join the arrows in this way. So I close them like that, in this circle, in that circle, in that circle, and the reds in this way, but then I have this. So I take this topology. That's just one topology. Because all this y minus 1, c6 minus 1 will cancel, because exactly because of the way I'm constructing the graph, the y's will cancel with the y minus 1, the c with the c minus 1, as long as I close the boundary like that. This is true. Because again, red go to red, so this means that C cancels C minus 1. And black goes to black, which means that Y cancels Y minus 1. Okay, so indeed, having this gauge degree of freedom implies much more than the peps. The two peps are the same in atoms. Here indeed, the same in any graph that is constructed in such a way. And now the theorem is that this is the only freedom, so that this is the data characterization. So if I consider all possible graphs respecting arrows and colors, and I ask that the two tensors gives rise to the same state in all those graphs, this is a characterization of having this gauge degree of freedom up to the limits. So formally, two tensors are gauge related now in this sense of the limits. If and only if they define the same peps for all graphs respecting arrows and colors. Moreover, it's enough to consider graphs with number of vertices with the scales e to the d squared of d. D is the one dimension. And we know that this exponential dependence cannot be improved in the sense that there are examples that require at least exponential. Okay. Whether it's e to the d or e to the d squared, this we don't know, but at least exponential is the. And the proof is, okay, sketching briefly and we say finish. So, two tensors are gauge related if and only if they give the same value for all invariant polynomials. That's the Smart's theorem. And now we show that invariant polynomials are generated by those induced by pairs of permutations. And these pairs of permutations are exactly those that define the graph. So one permutation for the red, one for the black. And now we use general values of the degree necessary to generate rings of invariant polynomials. Putting all this together gives this. Okay, 1. And for 2, we need just a particular example. Okay, so let me conclude. Okay, tensor networks have a nice gauge characterization. This allows us to also construct canonical forms, and this has nice privacy implications. So one may ask whether one can obtain gauge characterizations or canonical form for neural networks. There are options for that. And one thing I would like to point out is that we define this minimal canonical form, which is kind of the first canonical form that has been proven for peps. And one may ask whether the same nice properties that the canonical form had for 1D, for multi-spot state, extend to 2D. There is already some work showing that indeed this helps to improve stability in tensor networks methods. But there are other things one may look for, like improvements in the boundary correspondence and things like that. And just 1 minute to finish with a vague question like 5 minutes, which is the following. So there are some types of non-trivial topological phases of matter that give rise to pairs of tensors which are generally the same peps, but they are not case related. By the theorem, there must be some different graph which can tell the difference. And the question is if there is any connection at all between the type of topological order present in the state and the topology of the graph that allow to separate TRs. Both things that have the word topology, so maybe there is a connection, maybe there is no connection, but that, okay, it would be cool if there is. So that's it. Thank you very much for your attention.
Thank you very much, Mike, for this great talk. Questions?
Just what's known about synchronized processing networks? I mean, you said it's not so clear, but what's, I mean, is there some other states or is it?
Well, I must say, first of all, I'm not an expert at all in that level, but as far as I know, there is not. Indeed, there are recent results that at least point a bit in the opposite direction. There are results showing that somehow so there are these results showing that essentially, if you take neural network from some random point, you will find something which is very close to the global minima, close to any random initial point. So this means that somehow global minima are everywhere. So this means that it's very hard probably to tell the difference between all these super global minima. This is kind of behind the fact that they can change so well, but also show that the internal structure may be it's very hard to see. But as far as I know, it's not.
How do you interpret the NPS classifier? So
Okay, yes, no, okay, okay, you can, in one position, you have also an output direction, so and then this is a vector in a vector. MPS is just any vector in a sense of the vector space, and simply this vector space now is the set of mappings from, let's say, input to single variable. Now, this means that essentially, if you want, so in one position, here, this is an output. So this is the bit, 0, 1, the parts of dogs, and this is what it is. Actually, that's a function here.
when it's linear,
No, I mean, of course it's not because you have a tensor structure. So if you want this multi-linear in a sense. Yes. There was another question.
Any more questions over here or below? So if not, let's then